Welcome to another lecture in the course. The goal in this lecture is to learn about the gradient of a scalar, the divergence of a vector, and call of a vector. So let's start with the gradient. Okay, and I'll specifically write gradient of a scalar field. Okay, before we talk about gradient, let us let us recall that the slope of a function f(x) can be determined by taking the derivative of the function, of course with respect to x, that is, this slope is defined as the derivative of the function with respect to x. Okay, and you recall slope is the measure of the change in the function when x changes by a small infinitesimal increment, that is del x. Right, so that is the slope. And now for gradient, I want to think gradient of okay, let me write that this is one dimensional slope, right? And for a gradient, I want you to think about slope, but not one dimensional slope, three-dimensional slope, meaning that gradient gives rate of change in all direction. This slope over here gave you the rate of change in x direction. However, when you talk about gradient, it gives you rate of change in all possible direction. If your vector is three-dimensional, or if your vector has three dimension, then your gradient will give you rate of change in all three directions, x, y, and z. If your vector is two-dimensional, your gradient will also be two-dimensional. And the gradient for a scalar function, psi, the gradient of that function is defined as del psi equals to, this is unit vector along x direction, d psi partial psi partial x plus ay hat partial psi partial y plus ag partial psi partial z. Okay, now you might have a question, what is this thing, this inverted triangle? Okay, this thing, this inverted triangle is called nabla or del operator. Okay, it's not something you are multiplying or anything, it's an operator that acts upon of acts upon a vector, or in this case scalar, and that is defined as del equals to dy dx comma dy dy comma dy dg. So this is a vector, and sometimes you also write that arrow on top of the del, but if you miss, it's completely okay. Okay, this is an operator that acts upon a vector or a scalar function. In this case, this del operator is acting upon a scalar function psi to give you the gradient of the scalar function. Okay, all right, so that is your gradient in Cartesian coordinate. Okay, you can look your you can check your equation sheet to define gradient in cylindrical and spherical coordinate system. I'll quickly write them down over here. Del psi, and this is in cylindrical, that would be a rho partial psi by rho come, I'll use plus a phi 1 by rho partial psi partial phi plus a g hat partial psi partial g. Okay, and go check your your book, or every book have the formula, so I'm not going to write them down for the spherical coordinate. However, I'll work on a problem which is defined as the electrostatic field intensity E is negative del V, where V is electric potential at a point, and you have to determine E at 1 1 0 for V equals to V0 E negative x sine pi y divided by 4. Okay, it's our problem. You are given a vector, you are given a scalar function V equals to this, and you have to calculate the vector function E. So for that, you obviously have to take the gradient of V, and the good thing is this is in Cartesian coordinate system. So we'll proceed as E is negative del V. Okay, that means that is negative, and our del V in Cartesian coordinate is del V partial V partial x plus ay hat partial V partial y plus az hat partial V partial z. Okay, next we have ax hat as it is. We are taking the derivative of the function with respect to x, and therefore v0 sine pi y by 4 can come out of the derivative, and we take derivative of e raised to the power negative x. Okay, next is ay. Therefore v0 e minus x can come out of the derivative dy dy sine pi y divided by 4. And of course for the partial of v with respect to z is 0. Okay, let's go ahead and solve this. The derivative of e raised to the power negative x is e negative x times -1. Okay, and the derivative of sine is cosine. Okay, and we'll have pi by 4. Okay, that means that is, okay, I guess I made a mistake over here. Okay, this should be correct. And therefore we have ax hat v0 e raised to the power negative x sine pi y divided by 4 minus ay hat v0 e negative x cosine pi y divided by 4 times pi by 4. Okay, so that is our general expression for e, and we are asked to determine e at a specific point. So we'll substitute x equals to 1, y equals to 1. X v0 e raised to the power -1 sine pi by 4 minus ay hat v0 e -1 e raised to the power -1 cosine pi by 4 times pi by 4. Okay, so that is our solution, and let me rewrite that in this form. E raised to the power -1 is 1e, and we get a x hat sine pi by 4 is 2 by root 2 by 2 negative ay and we get pi root 2 by 2, but times 4 is 8. Okay, that is our final answer. Okay, that is a good example of problem solving for gradient of a scalar field. Okay, let's move to the next topic, which is divergence of a vector field. Okay, notice that when we talked about gradient, we talked about gradient acting upon a scalar function psi. However, when you talk about divergence, the nebula operator has to act upon a vector. And divergence, okay, if I have to define divergence, divergence gives you okay gives the measure of the growth or diminution d I m I n u t i o n diminution of the field, okay, at a given point. Okay, that is our divergence. To give you an example, if you consider a pipe, let's say you have pipe over here and water is okay flowing out of the pipe, okay, and at that point over there, at the opening of the pipe, the net divergence is positive. And let us take an example where the divergence is negative. And for that, if you consider a sink, let's say this is a sink, water flows onto the sink and it disappears, meaning that the divergence over there is negative. And an example where your divergence will be zero is if you take a point over here and if water is flowing through the point, but it's not coming out of the point nor it is going into the point, and at that time your divergence would be zero. Okay, so divergence is telling you telling you about the growth or the diminution of the vector of the um, quantity of the vector field at a given point. And divergence in Cartesian coordinate system is defined as del dot. Okay, this dot operator always means divergence. Del dot, let's say a given vector function a, and divergence again always has to be this del operator when it acts, or let me go back and I should say you can only compute divergence of a vector field. Okay, that was what I was meaning to say. Okay, now this becomes del partial x partial x plus del or excuse me partial a y partial y plus partial z a z partial z. Okay, since this is a vector function, you are isolating the x component of the vector, y component of the vector, and z component of the vector, and you are taking partial derivative with the respective component, and that gives you the divergence. And note that this is no longer a vector, the result is a scalar, whereas the result of the gradient was a vector because you had these a ax hat, a y hat, and a z hat, or a rho hat, a phi hat, a z hat. Okay, here you don't have them as a vector, therefore the result of the divergence is a scalar. And similarly you can divergence is defined for cylindrical and spherical coordinate. I'll encourage you to check the formula on your book, or you can check the equation sheet that I have uploaded in Blackboard to compute the divergence for other coordinate system. But for now, let us work on another example problem. Okay, example 2, which says determine del dot a, meaning divergence for a given vector a equals to xy ax plus 3g ay minus 5g square ag. Okay, so here you should first isolate the components of the vector. Ax is xy, a sub y is, or the y component is 3g, and a sub g is negative 5 g square. Okay, let's go ahead and calculate the divergence del dot a. So that is our partial xy divided by partial x plus partial 3g divided by partial y plus d by dg. The g component is 5g square, or negative 5g square, excuse me. Okay, and from here we get y. Of course, that is the second term is 0, and the third term is going to be minus 5 times 2, negative 10 g, and this gives us result as negative y minus negative 10 g. Okay, we don't have x, y, and z defined in particular, so we'll just stop here on the general form. Okay, so with that we covered gradient and divergence. Let us go to the third quantity that we are interested in today, which is the call of a vector field. Okay, so first thing, what does a call give? Call of a vector field okay, I promise to use a different color. Call of a vector field describes the tendency of the vector field to rotate or circulate about an axis. Okay, in simple word, it's giving you the tendency of the vector field to circulate around an axis. And the call of a vector field is defined as del cross A. Okay, and this is in Cartesian coordinate system, so that will be a 3 by 3 determinant ax, ay, and ag. Okay, I want some space in there, so ay and ag. Okay, we'll start with d by dx, d by dy, d by dz, and over here we write the x component of the vector, y component of the vector, and z component of the vector. And now we know how to solve this determinant. So let me do that quickly. So I like to give positive and negative positive. Okay, and therefore we get ax d by dy ag minus d by dg ay. okay, minus ay dy dx ag minus dy dg ax plus ag dy dx ay minus dy dy ax. Alright, so that is the call of a vector field. And again, let's work on an example, okay, to clear things up. And we are given over here a is a vector defined as y a x plus x a y, and you are asked determine del cross a. Okay, for that we know ax is that negative y, and a y is the y component of the given vector is x, and nice thing is 0. Okay, now del cross a, okay, you can start with the determinant, but I'll directly use this formula over there. Ax hat okay, so the g component, there's no g component, so the first term is 0. The y component does not have any g variables, so that is also 0. Okay, and for negative ay as it is, the g component is 0, so we don't have to worry about that. The x component does not have any g component, so that also becomes 0, and we have ag hat. Okay, the derivative of ay with respect to x is 1, and there is still that negative sign, and we need to calculate the derivative of ax with respect to y, which is negative 1. Let me have this square bracket over here, and therefore we get 2 times a g. Okay, that is the result of the call, and let's see what the result is explaining. So we are given a vector function. Let's say this is our x, this is y, g is somewhere over here, and it's saying that okay, it has a tendency to rotate around the g. Okay, that is what we calculated when we found this result. All right, so that is the calculation for call.